I will introduce first the general notion of this industry spotlight. It is organized by IEEE Santa Clara Valley section by Corporate Liaison Program. Mary Baker is part of the program committee. From this year, we also started being co-sponsored by the Computer Society chapter of Santa Clara Valley section. And with that, I will let Mary introduce our distinguished speaker.
Welcome, everybody. We are very excited to have Valerie Taylor as our speaker. She is our Argonne Distinguished Fellow and Director of the Mathematics and Computer Science Division at Argonne National Lab. She's also been on the faculty at 2 different universities. Most recently, I believe, Texas A&M. I think I have that right. Valerie, correct me if I'm wrong. But she was also at Northwestern University for several years. And she joined Texas A&M as the head of the department, I believe. Also, Valerie and I went to grad school together. So I have known her for many years. And so I have known that she's absolutely fabulous for many years. She has worked in modeling of parallel and scientific applications for a while now, although she's done several different things over the course of her career, concentrating on some different areas. And she is also the executive director of the Center for Minorities and People with Disabilities in IT. She will be talking today about energy efficiency trade-offs for parallel scientific applications. So we're very excited to have you, Valerie, our distinguished guest, and welcome.
Thank you so much, Mary, and thank you, Dejan. This was really great, and thank you for the invitation. And Mary, it's always great to see you. It's been a while, so. And let's see, I think I'll start, well, with sharing of my screen, I think, and we'll see. Okay, so am I good? I guess I can't see anyone, so if somebody could jump in.
You are good.
You are good.
Thank you, and thanks for that introduction. And so let me just go ahead and jump right in. And that is, so what I want to do in terms of looking at exploring the trade-offs with power and execution time is I want to start off with framing around the top 500 and also the green 500. And so with the top 500 and both top 500 and green 500, you're looking at executing the HPL or LINPACK benchmark. And so the top 500, you have the top machines. And so here, and this plot gives the top 25 machines from the top 500 list. And then also the plot in green, or actually in a little blue, it gives the top 25 machines on the green 500. And with the green 500 list, it's looking at energy, or actually power efficiency. So here, for the green 500, we're looking at gigaflops per watt. So if we look at the top machine on the top 500, we have the machine Fugaku that's with Riken Center. And so with Fugaku, we're able to achieve 442 petaflops. But in terms of power, this is 30 megawatts of power. And when we look at the efficiency, it's looking at about 15 gigaflops per watt, which makes it on about rank number 10 with the green 500. When we look at the green 500 list, this is the SuperPod, which consists of the NVIDIA DGX processors, or sorry, GPUs. And so with SuperPod, it achieves 2.4 petaflops, but it's at 90 kilowatts. And so its power efficiency is 26 gigaflops per watt. And for SuperPod, it's actually ranked 170 on top 500. So I give this framing to say we can see when we have significant power in terms of flops or performance, it's at the expense of significant power requirements. And so we're looking at that trade-off, looking at power, looking at execution time. Oftentimes, if we want to have or decrease the power, it's at the cost of an increase in execution time. And so just to give that framing, and let's see. Next slide. So to give that framing, it's around Power Stack. And Power Stack is a group, and it's a group of experts from academia, from the national labs, from industry, that's looking at a holistic approach with respect to power management. And so we had the opportunity to publish a paper together with the Energy Efficiency HPC, the State of the Practice workshop that was held at the cluster workshop in September. And so at that particular workshop, we were talking about looking at this particular framework and looking at actually going between the different levels. But let me take an opportunity to describe the framework, but much of my talk is actually going to be based on this framework and looking at some different components for the framework. So if we look at the framework, we're looking at a site, and here my background is focused on HPC systems. So we're looking at, for example, site level requirements for that machine. And the site level requirements, oftentimes with an HPC procurement, there's work that has to be done to actually upgrade the facility such that you can provide the power that may be needed for, let's say, a more powerful machine. And that's what I mean by that is a machine that's delivering more floating point operations. So you have the site level requirement. Then when you start to look at executing jobs, so you have the allocation of power to the jobs. And that may be, for example, depending upon how much power per node, how many nodes you have allocated to the job. And that's that with respect to looking at that power assigned to the job. You can also do looking at scheduling that's doing more power aware scheduling that may be looking at what are some of the power requirements of an application, not just its runtime. So, but let's look at the case where for job scheduling, you have some allocation of power for that particular job. And then that power may be distributed across the nodes in a way so as to reduce execution time. And I'll talk about that in a moment. At the application level, which is the level where we do a lot of our work, you're looking at we use hardware counters to give us hints for how to make the application more efficient. And so that's where we're doing the application level performance tuning and doing some balancing there. Then we can also go down to the component level, and that may be going down to, let's say, the processor level and doing some measurement and control there with respect to power. And so as you go down this particular hierarchy, you're inheriting power bounds from the previous level. So that is when you're looking at job scheduling, you're inheriting the power bounds by the site. When you're looking at the application, it may be looking at the power bounds imposed by the job scheduler for that particular application, and so on. And so when we start to look at, let's say, different tools, and sorry, let's see if I can get, okay, this will work, I'll use my mouse. So if we start to look at different tools that exist for the different components, we have GoPM, and I'll talk about each one, that's developed by Intel that's looking at job scheduling. We also have Pod, and Pod is also looking at job scheduling, but it's unique in terms of looking at coupled applications. So that may be applications that involve a simulation, also with possibly visualization or in situ data analysis or machine learning. And so POD is developed by Hank Hoffman at UChicago. Then we do work with the MUMMI, and that's for multiple metrics modeling infrastructure. And that's where we're taking hardware counters to give us hints on how to modify the application. And then there's also Encore Power Scavenger. And so this involves Mueller at NC State University, as well as Barry Roundtree at Lawrence Livermore, where what they're doing is looking at the processor and actually doing some tweaking for the Encore component of the processor. And so I'm going to spend time talking about these four components, which is really interesting in terms of the power management, and then wrap up with some challenges. So let's start to talk about GoPM, which is the Global Extensible Open Power Manager with Intel. And so with this particular power manager, it's actually developed in a hierarchical way where you have GoPM that's available at each of the compute nodes. And then you have some of the compute nodes that are also contain a GoPM aggregator. And then you have one compute node that includes a GoPM root. So what happens is that the GoPM root interacts with the, let's say, a power aware scheduler that allocates the power for a particular job. So what GoPM is looking at doing is actually, let's say, looking at synchronization points with an application to identify the node that's along the critical path, meaning it takes the longest, reallocate power to that node from other nodes such that now when you look at the synchronization points, you've now sped up that slowest link or that critical path, and you have all your processes that should get to the synchronization point much faster. And so what happens is that for GoPM at the leaf, you're actually sending back information to the aggregator, which goes back to the root, which then makes some decisions and redistribute. So the aggregator, where the root will distribute information along each level to its children, then its children will redistribute along to its children. So if we look at some results related to GoPM, so this is an example where they used the KNL cluster. And so here, what we're seeing is with the neckbone application, which is a hydraulics, a thermal hydraulics application. And so we can see here, for example, with this plot, we can see when the power, so this is a power cap, and the power cap is increasing. So when we have a small power cap, here we can see where for the baseline, it corresponds to a fair distribution, where each node gets a uniform distribution of the overall power allocated for that job. And here we can see in terms of the balancer plugin with GoPM, what happens now when it starts to redistribute the load. So you can see some advantages using the balancer plugin as you increase the power cap, where it's getting closer to the TDP for the processor. Then here, that's where you're seeing is about the same. And that's because it's not where now you have enough power allocated per node to actually give you good performance where the processes are getting to the synchronization point close to the same time. And this gives you an example too of where with GoPM, what it's doing here is this is the power, this is the execution time, it's normalized. And so with the power, it's identified that node 1 actually was along the critical path. It reallocated to have more power to node 1. The result is such that for that, when you're looking at the overall results, for neck bone is actually 2 phases, where it's actually doing 2 conjugate gradients of different problem sizes. And it's actually the second phase where you can see some performance gains where with the GoPM, you've now decreased the execution time where you've been able to reallocate that power within a given system. And so this is some of their work that was presented at the PMBS workshop in 2016. If we look at the work with Hank Hoffman and their work at U Chicago that was presented at SC19, that's based upon POD, which is the power capping for dependent distributed applications, it actually represents a follow-on to some of their earlier work called Power Shift. With Power Shift, it was looking at shifting power similar to GoPM. The difference with Power Shift is now looking at coupled applications. And that was the major difference. With POD, and actually with Power Shift, it was doing a lot of analysis offline, where it would take the profile of the application, do the analysis offline, and then feed that back into the system as an initial starting point, and then dynamically reallocate. What they're doing in the extension with POD is actually looking at 3 phases, where the first phase, they're going through and looking at what's a good configuration with respect to the node. And that has to do with, should they use both sockets or single socket? Also hyperthreads, should it be enabled, disabled? And then the memory controller, and that is, should they use both, one, or either? And so they actually do a lot of data collection and use a learning algorithm to identify what's the configuration for that particular application. And they do it for both applications. So this chart just gives you an idea of the configuration per application. But with these applications, some of them are scientific application. This is a visualization. This one is actually compression that they couple together. The second phase of what they're doing is to identify what's a good power cap. Now that they have the configuration for the node, what's a good starting point with the power cap? Then they're going through, the third phase is to work dynamically through execution. And they're doing all of this with POD. Again, it's working with coupled applications, but they're working online. So they don't have to do this offline analysis and have the profile. With POD, everything is online or during execution. And so, and this gives an example here in terms of a power cap where they had a 49 node system. One node is used for POD, the other nodes are used for the coupled application. And they compared again to a fair distribution. And so what we're seeing is when we have a small power cap, that's where POD does very well, where it's given like a 33% much better performance in terms of energy efficiency when it's looking across 15 coupled applications. And the coupling is between this group of applications. And you can see what happens going all the way to 9,600 watts, where it's about a 21% increase. And the harmonic mean is overall about a 28% increase in terms of better energy efficiency. Oops. And then lastly, one other system that I want to talk about is Encore. And then I'll get to our work. But with Encore, so Encore is this work that's done by Mueller at NC State and Barry Roundtree at Lawrence Livermore. And so what they're looking at is to identify with a core or with a processor, they can partition that processor into a core and Encore, where the core consists of the processors that you have and the multiple levels of memory. And the Encore consists of the last level cache. It also includes the memory controller and also the interconnect as well. And so that's what you're seeing here in terms of the Encore. The interesting aspect in terms of with Intel processors is that they have the ability to set the Encore frequency. And it's different than using RAPL, which is around the particular socket, this or the package. So the Encore just is around these components where they can set that frequency. And so what happens by default is that anytime there's activity, by default, it goes to the highest frequency, which can be very inefficient, especially for compute-bound applications. And so this gives an example of looking at the NAS parallel benchmarks. This is EP, which is more compute-bound. This is MG, which is more memory-bound. So here is where the Encore frequency is going down. And so here we can see as we decrease the Encore frequency, we're decreasing the package power as expected. And for this one, it's a small increase in terms of the completion time. However, for something that's memory bound, when the package power decreases, then we can see a significant increase in the overall execution time. What they did was to develop a state machine such that instead of just having it go to full frequency upon activity, that it gradually increases or decreases the Encore frequency based upon if, let's say, looking at IPC, if the IPC goes down, indicating that it may be due to access to memory, then that's when they start to increment the Encore frequency. So you're looking at doing that dynamically. And so what they found too is that the Encore, looking at different chips, that can take up about 30% of the real estate. When they actually did some results, they found, and it was using the NAS parallel benchmarks, that they were able to achieve about a 10% energy savings with just about a 1% slowdown in execution time. And this was just monitoring that Encore frequency. And if it's more relaxed in terms of the execution time, they can achieve about 14% energy savings with about a 5% slowdown in execution time. And these all things that become really important with respect to energy efficiency in terms of systems. And so what I've been describing thus far with GoPM, with POD, with Encore, is looking at different components. That is looking at the job scheduling, looking at impacting, for example, the processor, and in particular, working with the Encore component of the processor. What we've been doing is asking the question, are we starting off with an efficient application? And that is, can we gather information about how the application is executing on the system such that we can use that information to go back and make modifications to the application? And that's where what we do is to look at, and we have the Project Mummy, and we look at gathering information about the hardware counters. And so just to give you an example, and let me start off, sorry, I keep wanting to use my arrows, but I have to use my mouse. So this is an example of a power profile, for example, for CANDLE, okay? And so CANDLE stands for Cancer Distributed Learning Environment, which is looking at different components, looking at cancer treatment, cancer strategy. So it's looking at, and also the RAS pathway, and so in drug response, and it's using unsupervised learning, supervised learning, and also semi-supervised learning, dependent upon the strategy that's being approached. And so just to give an example too of the power profile, so this is an example that's executed on a single node of theta, where we have the data loading. We then have the time that's needed in terms of the training, validation, and you can see that requires significant power. And then we're seeing the power requirements in terms of the prediction, where the blue corresponds to the node power, the orange corresponds to CPU power, and then memory power. And going a little deeper about Mummy, where here, what we do is we start off with about 39 hardware counters. And the reason for starting with so many counters is that when we looked at different applications across different systems, there were different counters that became relevant, that helped in terms of the tuning. So we maintained still today in terms of getting information about 39 counters. It does require quite a few runs to get all the counters, but it becomes really important. And just to give an example, just to illustrate the use of counters. So I'll give an example where we did some work, and this was with researchers at Texas A&M, of doing earthquake simulations. With the earthquake simulations, it's EQ3 Dyna, and it's really doing a parallel finite element analysis. And so we can look at, what we did was the analysis of the mid-scale problem, where it's looking at the element size of 100 meters, which resulted in about 24 million elements in terms of the simulation. We executed the simulation on the Blue Gene Q machine at Argonne on Mira. And this just gives an illustration with respect to the counters. What we do is we use statistical methods to look at equations for runtime, for system power, CPU power, and memory power. And then we identify the counters that are the most significant. And usually those are the counters with the largest coefficients. We're also looking at using different machine learning methods. Right now, we're looking at ensemble methods to also identify the counters as well. But this, for example, with the EQ3 Dyna that's executed on the Blue Gene Q, so that's where vector instructions come up as important, and also branch misprediction. With vector instructions, what we found that really helps is actually looking at compiler options, and that's different compiler options to help us with the vectorization. in terms of branch miss prediction, oftentimes we did the loop unrolling. The question that came up is how much unrolling should be done, and we did that experimentally to determine a good amount of loop unrolling that's needed. When you do loop unrolling, you do pay a penalty in terms of increase in your instruction count. And so with this table, and I want to spend a little time here, with this table, what we did was to look at across some applications, EQ EQ3 Dyna, LULASH, which is a hydraulics application, BT and SP, which are part of the NAS parallel benchmarks, and also Candle. And it's across different systems. System G is an older system that was at Virginia Tech, where we were doing a lot of power measurements at that time. But you're seeing the different dominant counters. And based upon those counters, it gave us information to determine how to make modifications with the application. Sometimes, especially when it had to do with cache, we were looking at blocking in some cases, because what we could do when we analyzed the application is to have the counters be associated with different sections of the application. And so we instrumented different components, and we could actually map the counters back to those components as well. And that helped us to identify where to tune the application. And so in some cases, when we were looking at translation look-aside buffer, that resulted in us using a larger page size. So the counters helped us to identify, in many cases, it was modification to the application. In some cases, it may have been a modification with the system, like with the page size. And you're seeing different energy savings here. And the last two columns, what we're seeing there is, an arrow to indicate if we decreased in runtime or increased in runtime, or increase or decrease in terms of the power. And what we're seeing across all the applications is that we decreased in all cases in terms of the runtime. That was consistent. In these two cases, we also decreased in terms of power. And that had to do with a more efficient use of the memory. And so we could decrease the power that we were needed with the memory, while we were also decreasing the execution time. So in some cases, it can be done to decrease both. And we found that usually becomes associated with data layout and the memory footprint that's being used and how you're using your data. But it's been very interesting to work with the different applications. And what I want to do, just briefly, is to talk about some of our work we're doing now in the dynamic power capping space. And it's still looking at it from an applications view. And that is, so this gives an example of where the black line is decreasing, and it represents the package power. And we're seeing the package power actually stay within that, that static power cap. You're seeing the DRAM, oops, sorry. Let me just go back to that. You can tell I'm not the best with using the mouse. I'm used to my arrows, so I apologize. Okay. So, and here, we're seeing what happens with the execution time when we modify the power cap. I want to give this information here because what we're doing in terms of our dynamic power capping is based upon looking at the application and the application's use of the power. as opposed to identifying the critical path of different processes. We're looking at how the application profile changes. So this just gives an example of running on a Broadwell node with 2 sockets, looking at 18 cores per processor. And so what we did a lot of work on theta, and that's at Argonne, and it uses KNL. And so we looked at different applications. This is Lulesh, MG, and manyFE, which is a finite element application. And we looked at the different profiles, the power profiles that resulted, and tried to classify these power profiles. And that is, Lulesh is more of a smooth power profile. We classified MG as a bursty, where it's varying a great deal at a high frequency. And then manyFE, we classified as piecewise to say it's not high variability, but you have different sections for that particular application. Then what we did was to look at, and this is again with theta, and which is KNL. And so we looked at what happens when we decrease the package power. And the TDP, or the thermal design power for a KNL and on theta is 215 watts. And so we decreased it by 20 watts, and we can see, and this is the relative increase in the runtime. And so for the bursty, where you had a lot of fluctuations, we can see we did actually pretty good, and that was a 2 to 6% increase in execution time. When we went to 40 watts, it was 5 to 18, 60 watts, it was 16 to 70% increase. But it was the best in comparison to piecewise and the smooth, depending upon where that level is for the smooth. If you're going down below that, you can cause a significant increase in the execution time, which is what we're seeing. Then we wanted to see the impact in terms of the energy increase. And in some cases, it actually resulted in a decrease in the energy. And this is where with 20 watts, we actually had a decrease in energy in some case, and then it went up to a slight increase in terms of the energy. And the same with the 40 watts. And we're seeing when we get to smooth, it's a significant increase in terms of the energy, which tells us that for bursty and piecewise, that's an opportunity in terms of looking at doing some dynamic power capping with respect to the application. And so what we started doing, and this just gives some initial work that we've started, and that is, so we took the manyFE application and we wanted to make certain that initially that we can actually adjust the power to actually follow the profile of an application. And so what happens is that we're using the IPC, and we also use the number of retired instructions during the interval. And when we see a change, we go back up to the TDP, to the maximum power, and then we come back down based upon where we are. But we first overshoot and then come back down. And what we can see here is, again, similar of doing some overshoot, and again here. And so it tells us that we are at a good point of identifying throughout execution of an application that we can follow some of the power profile. And that's important because what we want to do next, and this is part of our future work, is to start to ask the question, what if a user says, I can live with about a 5% increase in execution time, or maybe a 10% increase in execution time? Then that gives us more of a range of what we can do with the dynamic power capping, because we can impose more stringent dynamic power capping throughout execution from the application standpoint, and stay within the tolerance. So that's the work that we're starting to do now, in terms of getting those results of setting that up to do the tolerance. So we're at the point of having a library where we can do that and working on some applications. So we're looking forward to the results in this space. So I want to, and just looking at time, so I'm wrapping up, staying within the 45 minutes. So I want to wrap up with some of the challenges around looking at energy efficiency, looking at performance power trade-offs. And that is, we can look at the level at the system level, at the job level, also looking at the application level and going down to the node level. So we talked about the work that's being done with GoPM and also pod that's at the job level. The work that we're doing with Mummy is at the application level. And the work that's being done by Mueller and also Roundtree is more at the node level, going down to the processor level. So if we start to look at some open challenges in this area, it has to do with now going across the different levels. And there's some work that's looking at that, of going across the different levels. But, a question that comes up is, exposing the right control parameters. So what information needs to go from the application to the job? Beyond just how is it doing with execution time? Are there other parameters that are important that can be used? And then also down to the node level, are there things that can be done at the node level? So if we go back to the Encore work that's now looking at the processor, to say, when you can reduce the frequency of the Encore portion, and you combine that work also with the work of pod and GoPM, you're now looking at the node level as well as the processor level. Then you can combine that and say, are we starting off with an efficient application, or are there things that we could be doing as well? And so considering that framework of going between levels, then it's also a challenge, especially considering heterogeneous resources. And that is, we've seen a lot of the work where it's really based upon CPUs and multi-cores. And now we're seeing systems such as Summit and Theta and Argonne, where you're having CPUs and GPUs. And you can imagine you can start to have CPUs, GPUs, and AI accelerators. And what does that mean also in terms of the framework and how you're doing that power management? And so, looking at those aspects. Then there's a lot of work too that's being done in the auto tuning space. And so are there opportunities with the auto tuning where that work is really focused on looking at execution time, where you're looking at data layouts, that you can automate that process of knowing some information about the application, using some machine learning to help you narrow the search space, to talk about what can be done in the auto tuning space. And maybe that can be extended also to look at energy efficiency. And that may also involve exposing the application workflow. Then there's the area where oftentimes we look at offline analysis, which is what was done with the initial profiling tool with Hank Kaufman. We do with Mummy, we're doing offline analysis. And then with their work with POD, GoPM, Encore is doing online analysis. Are there opportunities for that level of code tuning? And then, you know, the work that POD was doing, working with coupled applications is so important because we're now starting to see the trend of looking at more coupled applications, and that is looking at AI-enabled applications, in addition to applications coupled with visualization, coupled with in situ data analysis. And you can also have that going to feedback where it may go to some actuators to actually look at control. So you're looking at also increasing complexity with applications. So it's a range of open challenges that makes it very exciting in the space of performance power trade-offs. And I just want to take this opportunity to thank the many collaborators, including the Power Stack group and a number of collaborators in terms of the work that we do. And so I'll stop there, leaving on the slide with the open challenges and open for questions.
Thank you so much, Valerie. That was fascinating. And there are a lot of questions piling in the chat. We save them until the end, given the nature of how we're all connected here. But I would like to encourage people to speak up with their questions, or if you feel shy about doing that, then I can read your questions from the chat, either way. So I guess we shall open it up to people who are first willing to speak up to ask their questions.
Okay, and I have a feeling we have a great audience that's willing to speak up. So ready when you are.
Okay, I may be reading some of these questions.
Okay.
Okay.
Thank you, Barry.
I have a question, if you don't
So
mind.
some of the questions centered around the notion of what is the difference inside, you know, what you as a programmer can do for your application. If you are optimizing it for performance versus optimizing it for energy consumption, what are the examples where those two are opposed to each other, or what are the examples where those two are aligned with each other?
Oh, that's a really good question. And I think from an application standpoint, and this is based on my experience, I recommend, and that is getting information in terms of counter information. I think hardware counters are just so important to give you information about what's going on at the system level. And that can also give you information in terms of about how you're using different resources. And also you can get a power profile. So that information can be very useful in terms of, you know, as a programmer, understanding the application and what can be done. Because as a programmer, you know your application very well, okay? And you know the data layout, you know, why you're doing the sequence of computations, why you're doing the work that you're doing. But I think, you know, one question that comes up is understanding the underlying system to say, are there some things that you can do differently? And to get a hint about the things that you can do differently, that's where you need to get that information in terms of the underlying system. In terms of now saying, okay, should I just optimize in terms of execution time without a care for power, you know, and I just do my best to reduce the execution time? That, that will give you a reduction. It may give you a reduction in energy. However, in some cases where you're reducing your execution time, you may be using resources more, okay, in terms of reducing that execution time. So it depends upon what resources you're using to say it's going to give me better energy efficiency. So it's not always the case that the reduction in execution time compensates for the increase in power. It becomes system dependent on what you're doing. So
whoops, I was on mute. I think that does answer Dave's question, and he can raise his hand or something if that doesn't fully answer his question. But that I believe that was the answer. We're also seeing several messages in the chat about how excellent your talk is. Appreciating your presentation and thanking you for it. We also have a question from Jean asking whether anyone at your lab or your collaborators' labs, if any of them are looking at quantum computing computational improvements, and will these intersect with power efficiency?
Oh, great question. And that is in terms of the labs. So I would say all the labs are engaged in looking at quantum computing. And that is last year, DOE awarded 5 quantum centers. And the level of each quantum center is about 25 million per year for 5 years. So DOE has a significant investment in quantum computing. And I think there's some work, I know at Argonne, there's some work that's starting that has to do with looking at power efficiency around quantum computing as well. And that involves working closely with the vendors to get that particular information. But yes, it is, I would say all the labs are involved in the quantum space, and work is starting, I know at Argonne, in the power efficiency space with quantum computing.
That sounds like it would be a very interesting thing to watch going forwards. Let's see, with the first question, I kind of summarized several people's conversations in the chat. Let's see, I guess speak up now if you have other questions.
Okay.
I also have questions, so I hope you don't mind. So I'm wondering if you are, if over the time that you've been interested in this field and working on this field, if you've been seeing differences in the nature of the applications coming towards you. For instance, I'm not involved in this area, so a lot of this is very new to me, but I do encounter new problems in computational geometric modeling and things that are starting to be really intensive, especially because people who are actually doing the designing of the parts that we want to 3D print or whatever it is, want to be able to do fluid dynamic simulations and things like that, part and parcel with the design process. So that's an interactive application at the same time as having a very high degree of computational needs. And so I'm wondering if you're seeing things like that, if that's unusual, hopeless, a good idea, bad idea.
I think it's a great idea. I think you're starting to see, the applications that are interactive, that are coupled. You're also starting to see, especially with the science applications, where you may look at using, let's say, surrogate models for parts of the application that are computationally complex. And maybe you can replace it with a surrogate model in terms of depending on how much data you have access to. You're starting to see also applications that are coupled with sensors as well. You're seeing applications that are coupled with instruments. And that is, it may be where, for example, looking at a light source where you're doing some in situ data analysis, at the data that's generated at a light source and having those results feed back to steer the light source, such that you can get the analysis that's desired, and it's not where you have to, get the data, do offline analysis, come back and then steer the light source to do a finer granularity of what's desired. So you're starting to see some things that are coupled in the way that you're describing, that, where there's some feedback in the loop to help with the steering. And some of that, and it's so interesting because I think you can almost imagine too, where you're doing some in situ analysis, the steering, that steering may involve optimization. You may be doing some machine learning in terms of reducing the search space that you're looking at. So it's I get excited in terms of what's there, that you just kind of go, it's always exciting and something to work on. It's never a dull moment. So so we're seeing different applications, and also the systems, and the systems are changing. And that is, so for example, when we initially started doing work with power, which, and that's where we started doing some work, I would say with Kirk Cameron at Virginia Tech, we were doing the power measurements using DMMs, of having probes on the boards to do the power measurements. It wasn't where we had access to, counters to get the power measurements. And so you see how things have evolved, where you now have access to a power management structure. Like, for example, with Intel, you have access to RAPL, where you can go in and set power bounds, and it's doing the dynamic frequency scaling based on those power bounds. You have access to a lot of the counters and a lot of the power monitoring, as well as the execution time monitoring and the monitoring with the different resources. So you have that information that becomes available that you can then use in many different ways to give you better efficiency. And I also want to mention too, it's interesting because I think when HPC centers get new machines, and you look at the power requirements, when you're talking about something that's 30 megawatts, it's a significant amount of power. And oftentimes with the centers, they may have to go through and actually have construction that's done to provide the power that's needed for that center. So it's the increases in the power, it can cost you in terms of the overall infrastructure, and then it can cost you in terms of the monthly and annual cost with respect to keeping that center running. So it gets expensive.
I imagine it does, yeah. The levels of power consumption and flops that you're talking about are so far beyond the things that I end up doing in my area. So I see there's a whole different world out there. I want to ask again if anybody in the audience wants to raise their hand or speak up with a question.
Yeah, I have a question. First of all, thanks for the great talk. So I was wondering that, have you looked at the power consumed by interconnects because of the data movement, and how much is that of a concern in large simulations?
So that is a very interesting, and I was having a discussion with someone earlier today about interconnects. And, and the question that comes up is also the power measurements for interconnects. And that is, we have access to the power measurements, the package power